Hello again, welcome back. We are looking at gas variables today. Gases have some pretty unique properties, make them much different than solids and liquids. So we're going to spend a whole activity on gases, looking at their variables, meaning when we're looking at things like volume, pressure, temperature, and how they relate to one another. Okay? Basically, we're going to be looking at the variables that describe a gas. Okay, and we're going to be seeing how they're related. How are those variables related one to another? Okay. As mentioned, we're going to be focusing on pressure, volume, temperature, and quantity or number of particles. And we know from a previous video that when we're talking in chemistry about number of particles, quantity, the value that is often used is a mole. Okay, remember that is just a number. It's 6.022 times 10 to the 23rd. Huge number, but it's just a number, a quantity that is often used in chemistry for anything. In this case, particles of a gas. For pressure, we're going to use capital P, volume capital V, temperature capital T, and moles is going to be a smaller case n. In Model 1, we have several different containers or flasks, and they are non-flexible, meaning they cannot expand. It's not like a balloon that can get larger or smaller. These would be like glass tube or glass flasks, glass containers. They're not flexible. And in experiment A, they are telling us that they're adding more gas. So if you compare container A1 to container A2 to container A3, you'll notice that the number of particles is increasing as you go from 1 to 2 to 3. Down here we have information about volume, external pressure, internal pressure, and the temperature, and seeing how those are affected as you add more and more particles to a non-flexible container. In experiment B, notice we've got 3 containers again. They are also non-flexible, but this time we are heating the gas. The number of particles is not changing. You have the same constant number of particles throughout container B1, B2, and B3. And again, we have information down here about volume, external and internal pressure, and then temperature. In Model 1, what does a dot represent? That is going to represent a gas particle. Or I suppose you could say it represents a whole mole of gas particles. It's up to you. Name 2 materials that the containers in Model 1 could be made of, or made from, that would ensure that they were non-flexible. Well, they could be glass, for example. I just mentioned that. They could be metal. They could be some substance that is not going to expand or contract. The length of the arrows represents the average kinetic energy. Average kinetic energy. Kinetic energy, we usually put capital K, capital E. Average, we put a line over there. That is the average kinetic energy. That's the length of the arrows. And that is the average kinetic energy of the molecules in that sample. Which gas particle, pressure, volume, temperature, or number of particles, moles, is most closely related to the length of the arrows in Model 1? Well, if we look back up here, you'll notice that in experiment B here, as you heat the gas, as you increase the temperature of those particles, the arrow is going to increase in length. So the arrow is representing the average kinetic energy, and that is directly related to the amount of heat that is inside those containers, or we measure it with the variable called temperature. So this would be temperature. So kinetic energy, the average kinetic energy, is proportional to the temperature of the particles. Complete the following table for the 2 experiments in Model 1. So if we look here, experiment A and experiment B, complete the following table: independent variable, dependent variable, and controlled. So let's just talk about these really quickly. The controlled variable is the one that you are keeping constant. You're not changing it throughout the experiment. The independent variable is the one that you are changing, that you have decided to alter and to manipulate. The dependent variable are all the other variables that you have allowed to change. You're not keeping them fixed. You've allowed them to change and they change accordingly how they are related or how they are connected to the independent variable that you are manipulating. So if we look back up here in experiment A, we're looking for independent variable, dependent, and control. In A, first of all, let's look for control. That's kind of easy because you're looking for things that don't change. Volume is not changing. These containers are always the same volume. A1, A2, A3 have not changed. So volume is control. External pressure is not changing. That means the atmospheric pressure. You're doing this in a room where the atmospheric pressure is not changing. It's not changing dramatically, and so that is being controlled. The internal pressure, that is changing, and the temperature is not changing, though we're keeping that constant. That is controlled. So internal pressure is changing, and what else is changing? Well, we're adding more gas. We were told that we're adding more gas up here, so the number of particles. Which one are you having the control over? You have control over adding more gas. So somehow you are adding more and more particles in order to see how the variables are affected. And in this case, you're seeing specifically how internal pressure is affected. So N, the number of moles, is your independent variable, and your internal pressure, the pressure, is your dependent variable, and then all of these three are your controls. Let's look down here. In this case, heating the gas. So you are increasing the temperature. You have chosen to do that. So temperature is our independent variable. What is changing down here? Well, you'll notice that what is changing is not the volume. That is a control again. Not the external pressure. That means the pressure outside the container. That is controlled. But what is changing is the internal pressure. So the internal pressure is changing, and this would be your dependent variable. The temperature we already mentioned, that is changing. You've chosen to change that. Maybe you're putting this on a hot plate here, and you're cranking up the hot plate. So the dependent variable is your pressure dependent variable. Okay? So that helps you fill in the table or check yours that you already did. Of the variables that were controlled in both A and B, one requires a non-flexible container. Name this variable and explain why a non-flexible container is necessary. So we're looking for the controls here. In order for something to be controlled, it has to have a non-flexible container. Well, that would probably be our volume. Okay? So notice up here, in order for this volume to stay controlled, we need a rigid container that is not going to expand when you put more and more particles in here. Unlike a balloon, you put more and more particles, air particles into a balloon. You blow into it, it's going to expand. But we need a non-flexible one in order for the volume to stay constant. And therefore, volume would be a controlled variable. Pressure is caused by molecules hitting the sides of a container or other objects. That would mean like the inside walls of the container, when particles slam against them, that is how pressure is created. The pressure changes when the molecules change how often and how hard they hit. So more frequently and with more force, you're going to increase the pressure. A non-flexible container is needed if the gas sample is going to have an internal pressure that is different from the external pressure. Okay, non-flexible. Non-flexible means like a glass flask that is not going to expand. If a flexible container is used, the internal pressure and external pressure will always be the same because they are both pushing on the sides of the container equally. If either the internal or external pressure changes, if it's flexible, the flexible container walls will adjust in size until the pressures are equal again. So that would be like if you had a balloon and you put air into that balloon is going to get bigger, and always the internal pressure and the external pressure are going to be equal. That's the volume that it's going to stop at. It's going to get bigger until internal pressure and external pressure are exactly equal. Okay? Name the two factors related to molecular movement that influence the pressure of a gas. So the two factors that are related to molecular movement that are going to influence the pressure of a gas. So as mentioned up here, pressure is how often and how hard. So we're looking at the how frequently. Okay, so the number of two factors related to molecular movement. So we're looking at how hard and how often. So this is force and this is frequency. As you increase the temperature, they're going to have a little more kinetic energy, those particles, and so they're going to increase the force with which they slam against the inside of the container. If you add more and more particles, then they're going to be hitting the sides of the container more frequently. Provide a molecular level explanation for the increase in pressure observed among the flasks of experiment A. Well, let's remind ourselves, in experiment A, we had an increase in number of particles. So that is going to increase the pressure, because as N is moles, N is the number of particles, as N goes up, then the pressure is going to go up. Why? Because you have more particles, means collisions or more frequent collisions against the inside of the wall. All right? That's going to increase the pressure. Provide a molecular explanation for the increase in pressure observed among the flasks of experiment B. Well, this one, as you increase the temperature, the pressure goes up. Why? Because particles have more energy. If they have more energy, the force with which they are hitting the wall is going to go up, and pressure therefore is going to go up as well. Okay? So this temperature gives them, if you add more heat, you're giving the particles greater kinetic energy, and they're going to slam against that inside a container with greater force, therefore increasing the internal pressure. Predict what would happen to the volume and internal pressure in experiment A of Model 1 if a flexible container were used. Well, if you have a flexible container and you keep adding more and more particles, the balloon, let's say, is going to get bigger and bigger and bigger because you're adding more and more particles. But the internal pressure and the external pressure are always going to be equal, because inside pressure, outside pressure is going to be the same. This will continue to expand until the internal pressure and the external pressure are the same. Once they are, it stops expanding and it has gotten back to that original pressure that it was at. Fewer particles are going to exert less pressure inside. Okay? But as you add more and more particles, this has to expand to try to relieve some of that pressure. So now you've got the number of particles here, greater particles, but since you have a greater surface area inside, they are hitting with the same type of frequency as they were before. And now the internal and external pressure are the same again. Predict what would happen to the volume. So did I answer that question? Yes. What happened to the volume? Volume is going to increase. Internal pressure is going to always get back to where it is equal to the external pressure. It's going to be the same as it was originally. That is, remember, that's for a flexible container, like a balloon. Remember what would happen to the volume, predict what would happen to the volume and internal pressure in experiment B of Model 1 if a flexible container were used. Again, a flexible container, what's going to happen to the volume and internal? This is experiment B now. This is where we're increasing heat. Heat is going up. Temperature is going up. Again, if it's flexible, well, as you increase the temperature, the particles are going to have greater kinetic energy, and they're going to slam against the inside wall of the balloon with greater force. And that is going to cause the balloon to expand. It's going to get bigger, it's going to get bigger and bigger. Again, it's going to keep getting bigger and bigger, and it's going to stop at a certain size until it gets back to this original internal pressure. Okay? So these particles are going to slam against this inside of the balloon, and as a result, they're going to keep doing that, keep expanding the balloon until the inside pressure is equal to the outside pressure. These two have to be equal to each other, and that's where the size of the balloon is going to find its equilibrium. Okay? In each experiment in Model 1, determine the relationship between independent and dependent variables and write an algebraic expression for the relationship using variables that relate to the experiment. Here are the variables that we're going to use. Use K as a proportionality constant. All that means, if you're not familiar with proportions, is if two things are related, meaning one goes up and the other goes up, or one goes up and the other goes down, if they're related, they may not be equal to each other. Okay, like X and Y, they may not be equal to each other, but there may be a relationship. As X goes up, maybe Y goes up. Or as X goes up, maybe Y goes down. Or vice versa. As Y goes up, X goes down. So you can't really say necessarily that X and Y are equal, but you can set them equal if you have some other number, we'll call it K, and that K then is going to be the factor that then is going to set them equal. So this is called your proportionality constant. All it's saying is that basically this ratio X over Y, if that's a constant, then if X goes up, Y goes up. That is a direct relationship. And if X times Y is constant, that means as X goes up, Y's got to go down to keep that product constant. This is an indirect relationship. Okay? So direct simply means that when one goes up, the other goes up. Indirect means that as one goes up, the other goes down. So let's figure out what we have here. In experiment A, what did we change again? We changed the number of particles. That would be your N. And what changed is the internal pressure. Internal pressure, P. So they're not equal. One goes up, the other goes up. We're going to set them equal with a K here. All right? Actually, we probably could write this as P equals Kn, because that n is the one that's being manipulated. That is your independent variable. Okay, so you might see it better as P equals Kn. And in so this is, I'm kind of answering the second part here. So this is a direct relationship, and this can go down here. P equals Kn. Then experiment B, it was the heat or temperature. So as temperature went up, then we saw the internal pressure also increase. This K and this K are not the same necessarily. They're two separate Ks, but I'm just using the same variable for that proportionality constant. So this also is direct. Okay? All right, we have model 2. So this time we're going to look at some other variables. And we have here adding, okay, we're doing the same thing, adding more gas, but this time notice the difference, flexible, flexible, flexible. So we're going to add more gas, and notice that the balloon is getting bigger. So that means the volume is changing here. Those would be your, I'm probably going to answer the question here. You're going to see a table down there below. So here we're adding more gas, so N is our moles. That's going to be your independent variable. Your volume here is what is your dependent variable. That's what's changing. External pressure, controlled. Internal pressure, controlled. Remember, those are always going to get to a point, it's going to get to a volume where the internal and external pressure are the same, and temperature is controlled. Experiment D, heating the gas. Again, flexible container. Notice that the size of the balloon gets bigger. So this time, temperature is your independent variable. Volume is your dependent variable. and pressures are controlled, and temperature is, as we already mentioned, your independent variable. This time, reducing the external pressure of the gas. So what that means is you're going to take this balloon, and in order to tie it off here, you're going to take this balloon and you're going to go somewhere where the external pressure is less, like you're going to go higher and higher in the atmosphere. So maybe you're going to go from the bottom of a mountain where the pressure, external pressure, is a certain amount, like at sea level, 1 atmosphere, and then as you go to the top of a mountain, the air is thinner, and so the air pressure is less as you move further up in our atmosphere. Okay, so this is reducing the external pressure. So external pressure is your independent variable, and notice what is changing: the volume. That is your dependent variable. The external pressure, we already said, that is going to go down. That's your independent. Internal pressure is also going to be matching that. That's why a flexible container is going to get bigger, is because the internal and external pressure always match each other. And the temperature is a control. So consider the gas samples in Model 2. Name 2 materials that the container could be made of that would ensure they are flexible. Well, one obvious one I'm just going to mention, like a rubber balloon. Okay, that would be a simple example of something that's flexible. What is always true for the external and internal pressures of gas in a flexible container? They're always going to be equal. That balloon is always going to reach a volume such that the internal and external pressures are equal. That's where it's always going to stop at as far as its volume. Complete the following table for the 3 experiments in Model 2. Independent variable, dependent variable, control variable. So I already did this. Independent variable. So actually, well, I'll just fill it in really quickly for you here so you can check. Independent variable in C, okay, number of moles. Dependent variable is volume. Control is going to be temperature and external pressure. For experiment D, the independent variable was the temperature, volume was the dependent, and number of moles and external pressure are your controls. For E, it was external pressure is changing, the volume is the dependent one, and number of moles, number of particles in there. Remember, the balloons are tied off, and temperature are your controls. Provide a molecular level explanation for the increase in volume among the balloons in experiment C. How often or how hard are the molecules hitting the sides of the container? So again, what we need to talk, what it's asking you is talk about the molecules. What are the molecules doing? So that the volume is increasing in experiment C. If we look back up here at the experiment C, why is the volume increasing? That's because you're adding more and more particles. Okay? So basically what's happening here is as the number of particles increases, the volume is going to increase because you have greater collisions. Those particles are colliding against each other at the molecular level. I'm trying to help you think. At the molecular level, those particles are really slamming against each other with greater frequency, and therefore the volume of that balloon has to increase. Okay? Provide a molecular level explanation for the increase in volume among the balloons in experiment D. In experiment D, you've got the volume is increasing because of temperature. Well, in this case, you've got as temperature increases, the kinetic energy, the average kinetic energy of those particles is going to increase. That's actually the definition of temperature. It is the measurement of the average kinetic energy of the particles. So your kinetic energy increases, and therefore they're going to press against the inside of the balloon with greater force, forcing the balloon to expand until the internal and external pressure is going to match again, meaning you're giving those particles more space, and the internal pressure now is going to come back to what it was originally. Provide a molecular level explanation for the increase in volume among the balloons in experiment E. In experiment E, we are reducing the external pressure. Well, reducing the external pressure means that it is going to allow the particles inside the balloon to push outward. They're going to continue to push outward, but now the external pressure is going to reduce. So if you've got, imagine this is the wall of the balloon here, you've got pressure internal pushing here, and you've got pressure external pushing, and they match. And now all of a sudden you lessen this. Okay, this force here is going to be smaller than it was before. So all this internal pressure then does not have to push as much as it did before, and as a result, well, you're going to have the same particles here. As a result, it's going to expand because this external pressure has now reduced, and the volume is going to have to increase in order to give these particles more space to bring the pressure down to match that reduced external pressure. Okay? Volume increases. Compare experiment A of Model 1 with experiment C of Model 2. How are these two experiments similar, and how are they different in terms of variables? So we're looking at A and C. Well, A, remember, it was a non-flexible. C, we're working with flexible. Okay? And in C, it was the number of particles as the same with A. Both of them are increased in number of particles, but one is flexible, one is non-flexible. So as a result, you saw that in experiment A, the volume did not change, whereas here, the volume is changing. Okay? And in experiment A, it was the pressure that changed because we didn't allow the container to expand. Whereas here we are allowing the container to expand, so the pressure is always going to be the same. It is the volume that is changing. Compare B and D. Same thing here. One is non-flexible, one is flexible. As a result, what happens here? In both of these, I believe we are changing the heat, we're increasing heat. But in B, with the non-flexible one, if you increase the temperature, the pressure is going to increase because you're not allowing the container to expand. Whereas here, it is the volume that is going to change, and as the volume changes, and it's allowed to change, the pressures are going to, internal and external, are going to remain constant. Okay? E, if that was done in a non-flexible container, would there be any change to the internal pressure? The answer is no. If you change the external pressure, the inside pressure of a glass flask, if you've got it capped, okay, assuming you've got some type of lid on it, then the internal pressure is not going to change. Unless you change it so drastically that the internal pressure is so much of a difference between internal and external pressure that it basically explodes and the non-flexible container cannot hold it, cannot contain it anymore. Okay? For each experiment in Model 2, determine the relationship between independent and dependent variables and write an algebraic expression. Okay, we're going to do exactly what we did before, but now we're focusing on Model 2 here. And as we do so, let's remember what our variables are. We've got pressure, volume, temperature, and number of particles. Okay? So, direct or inverse, we're going to try to identify that first, and then we're going to see if we can come up with an algebraic expression. So, if we look at experiment C, let's remind ourselves in experiment C, we have number of particles and volume. This is for a flexible container. So as you add, and this is going to be a direct, by the way, as you add more and more particles, the volume is going to increase. So volume is going to go up as number of particles goes up. The next one, D, was temperature and volume. So as temperature increases, the volume increased for our flexible container. So this is direct as well. And this is volume is directly related to temperature. And then the last one, this would have been external pressure. External pressure, as we change that, the volume is going to change as well. This time, the external pressure is going down, the volume goes up. So that is an indirect, or they call it inverse, same idea. Okay. So as the volume is going to increase as the external pressure decreases, you can write it like this, or you could also write it where you've got a ratio here. So you could write it as V is equal to K over external pressure. Okay? Oh, sorry, not P, V. My apologies. Okay? The three samples of identical gas molecules below all have the same internal pressure. Rank the samples from lowest temperature to highest temperature and add arrows of appropriate size to illustrate the average kinetic energy of the molecules in the sample. Okay, so what they're saying here, you've got three samples, all the same gas molecules, and they all have the same internal pressure. Rank the samples from lowest temperature to highest temperature and add arrows for appropriate size to illustrate the average kinetic energy. Remember, I just mentioned that temperature is a measurement of the average kinetic energy of the gas particles, or any particles for that matter. Well, let's see what's happening here. Notice, let's compare two at a time. These two are the same size, let's call them, say they're balloons, same size balloon, but one of them has fewer particles. So these 4 particles right here are doing the same job as those 8, which means they probably are pressing against the inside of the balloon with a greater force, which means they have a higher temperature. These must be have a higher, more energy, have a higher temperature. I'm gonna just number these 1, 2, and 3. Okay. Let's compare these two, 1 and 3. 1, 3 is larger, same number of particles. So 3 must be pressing with greater force than 1. Okay? And if I was just to assume that balloon 3 is twice as big as balloon 1, then they probably have twice the kinetic energy. So it looks like 2 has the least kinetic energy, lots of particles doing the work as compared to balloon 1 here, that only half the number of particles are doing over here in balloon 1. So if I was to kind of rank these as far as kinetic energy, balloon 2 would have the least kinetic energy. Balloon number 1 would have energy that's about double that, and balloon 3 would have about double number 1. Okay? So this is lowest, this is highest, and this one is in the middle. Okay? Alright, so what we're going to do here is we're going to come up with, kind of summarize all of this and come up with our equations that are going to help you understand all of these gas variables. Draw a sample of gas that is colder than all 3 of the samples in question 21. Explain why you are sure that it is colder. Okay, basically, if I was to do this, my sample would have to have, let's say easily, if this is the coldest, I could draw the same size. It's not quite the same size, but let's say it is, and I would just put more particles in there. Basically saying that all of these particles that I'm putting in here have the same internal pressure as fewer particles here in balloon number 2. Therefore, they must have less energy here in balloon number 4. Okay? All right. We've been talking about gas variables and the relationship between all of these. Again, number of particles, temperature, pressure and volume is really what we're looking at. Okay? It says here, 4 of the relationships you investigated in Model 1 and 2 are named after scientists who discovered the relationships. Use the internet or your textbook or some other source to find the scientists who discovered these laws, okay? And we're going to write the algebraic expression that describes the law in the box below each name. So I'm just going to give these to you. Robert Boyle, he found the relationship between pressure and volume, and he found out that as the pressure increases, that the volume is going to decrease, or as the pressure decreases, the volume is going to increase. This is the experiment, I think that was E, okay? Or D maybe. I don't remember. A, B, C, D. Oh, that's E. Yep, this was experiment E, I think. Okay? Charles' law is the relationship between volume and temperature. That is, temperature goes up, volume goes up. And then Montone's, he was pressure and temperature. So pressure and temperature, as temperature goes up, then the internal pressure is going to increase. This would be like for a non-flexible container. And then Avogadro said that as you have more and more particles, that's going to increase your volume. You may remember from a previous video we talked about Avogadro. We talked about Avogadro's number, and remember he came up with the discovery that for any gas at standard temperature and pressure, 1 mole of gas is going to occupy the same volume. So this is the relationship he was talking about. That volume was 22.4 liters, I believe. Okay? Alright, chemists combined all of the relationships seen in Model 1 and 2 into one law called the ideal gas law. This is a great gas law. This takes care of everything, by the way. It is one equation that describes a gas behavior and the relationships among all 4 of the variables. In the ideal gas law, the proportionality constant is represented by a particular letter. We're not going to use K anymore. It's going to be R. Okay? So, circle the algebraic equation below that best combines all the relationships you identified among these 4 variables. Well, let's just see if we can remember what the relationships are. So, pressure, volume, temperature, and number of moles. So, let's think about this. If number of moles increases, then we know that the volume is going to increase. So those should be on opposite sides. Volume and moles. As moles increase, the volume is going to increase. We want them on opposite sides of the equal sign. Okay? Also remember that when we increase the temperature, that also increased the volume for a non-flexible. So they should be on opposite sides. Okay? Temperature and volume. Remember that as you increase the temperature for a non-flexible container, the pressure, the internal pressure increased. So those should be on opposite sides. Temperature and pressure. Okay? And then we need to set them equal. Okay, right now if I don't have an equal sign, they would be proportional. You can use that symbol for proportionality. If I want to set them equal, I need some constant, and they told us we're going to use capital R for that. So we got PV equals, and then these 3 variables I actually going to rearrange those just so it sounds a little bit better. PV equals NRT. Okay? PV equals NRT. This here is the relationship between all 4 of the variables, and it's showing you how you can always set those up. Okay? And the relationship is simple because if I divide by N and T, this constant R is equal to PV over NT. Okay? So PV over NT is a constant. That's a constant ratio. Which means a problem might be given to you where you have a set conditions. You have set pressure, volume, number of particles, temperature, whatever, and then something changes. Temperature changes, and you want to find out how the other variables are affected. Well, often we'll look at just 2 variables at a time, but we've got 4. Well, that's okay. If you need PV over NT, and you need to equate that to another case where the temperature or volume or pressure have changed, let's put a 1 on all of these for case 1, and then a 2 on all of these after the change here, after something's happened. Now we have a second group here, number 2. These have to be equal because they're equal to the same constant. So all you do is you plug in the ones that you know from the first condition, and you plug in the ones that you know for the second condition. If any of these variables don't change, you can just cancel them out of this proportion. For example, if you've got a situation where they say volume is constant, just cross it out. You don't need it in the equation. Or if they say temperature constant, okay, I don't need it. And now it's just P over N1 equals P over N for 2. And I can just solve for whatever one is missing. Okay? So this proportion right here, P1 V1 over N1 T1 equals P2 V2 over N2 T2. This will help you solve anything when it comes to the gas variables. All 4 are right there. Okay? And then this is the ideal gas law, where if you have maybe 3 of these, but you need to find the 4th, you could use this along with this constant R, which would be given to you, to find out any of the missing variables given the other 3. Okay? So this equation here, PV equals nRT, is helpful when you're given 3 and you need to find the 4th. This equation down here is helpful when you've got something that's changed. One of the variables has changed, and you want to find out how does that affect any of the other variables. Remember, if one of the variables or more than one of the variables doesn't change, just cross it out of that equation. Okay? All right. I hope that's helpful. Gas variables, very powerful unit here on gas variables, because gas properties are quite different than other substances that are liquids and solids, and so we committed a whole activity here just on gas variables. And we're going to see probably this ideal gas law later on as we continue our course. All right, I'll see you in the next video.